Okay, assalamu alaikum. In our last lecture, we completed the external flows. So what we are doing right now is convection, right? So convection heat transfer. So convection heat transfer from the external flows, whether the flow is over the plate, or the flow is over the tube, or the flow is across a sphere, or the flow is across a bank of tubes. We studied that and we completed that topic, okay? And that is the convective heat transfer through external flows, for external flows. Now we move towards the next chapter, which is chapter 8. And in this chapter, we are going to study the convection heat transfer in internal flows. So that's the internal flow, okay? From your book of Fundamentals of Heat and Mass Transfer by Incropera and Dewitt. So let's okay. So these are the topics that we are going to cover in this chapter: hydrodynamic considerations, thermal considerations, energy balance, laminar flow, convection correlations for turbulent flow, for a pipe case. The most important is the pipe case. Normally, when we are considering the internal flows, so convective heat transfer by internal flow inside a pipe is the most common and the important parameter and thing for us, because most of the time we use pipes, okay, in heat exchangers. Then in the end, we are also going to deal with a little about convection mass transfer, okay. So there are some topics that we are not covering, okay, so it's reading by student. So if you want to go through it, you can go through it through the book. Okay. Okay, so let's talk about introduction. Recall that an external flow is one for which boundary layer development on the surface is allowed to continue without external constraints. So if you remember, in case of the external flow, you had an external flow, okay, over the plate or whatever, over the pipe or sphere, and the boundary layer keeps on developing, and it keeps on developing until it is fully developed, or it is developing, right? So the thing is that it is not constrained. Nobody is stopping it to develop, right? But in case of internal flows, what happens is that in case of internal flows, if we have a pipe like this, let's say this is our pipe, okay. So in case of internal flow, if this is our pipe and the flow enters the pipe, so the boundary layer will start developing at the surface of the pipes, right? And so it will start developing in all directions, and then it keeps on developing until a time comes when all will merge together, and after that it cannot further develop. It is then fully developed because it is constrained by the other boundary layer which is developing from the other side. So boundary layer is developing from the surface in all direction, and it keeps on growing from all direction until a time comes then they merge together, and that's how they are constrained. They are not allowed to develop after that. The boundary layer is constrained by the boundary layer developing it from the other side, right? So that's the difference between the external flows and internal flows. In the external flows, boundary layer keep on developing and there is no constraint. Nothing is stopping it to develop. But in the internal flows, it will develop, and after a certain time it is fully developed because it is constrained. It cannot develop furthermore. You get the idea? So these things which I highlight are important here. I might question you out of it, okay? So in the external flows, the boundary layer development on the surface is allowed to continue without external constraints, okay? In the internal flow, they are constrained by the boundary layer itself, which is developing from at the other side. In contrast, an internal flow, such as flow in a pipe, is one for which the fluid is confined by a surface, okay? Hence, the boundary layer is unable to develop without eventually being constrained. automatically it gets constrained because this is bound by a surface. It's a close, it's a closed environment. Okay. The internal flow configuration represents a convenient geometry for heating and cooling fluids. Okay. Anyways, this is the objective. So let's talk about the hydrodynamic consideration. What does hydrodynamic consideration means? Hydrodynamic consideration means, like for example, in the case of external flows, we said that if we put a plate and there is flow across it, so there is disturbance in the field, and that is going to develop a boundary layer, which is of the velocity boundary layer. Okay? So hydrodynamic constraints deal with the velocity boundary layer. Okay? Hydrodynamic constraints deals with the velocity boundary layer. Similarly, in case of the pipe, the velocity boundary layer is developed because of the hydrodynamic constraints. So hydrodynamic for velocity, thermal for temperature. Get it? Hydrodynamic for velocity, thermal for temperature. So when considering external flow, it is necessary to ask only whether the flow is laminar or turbulent. That's, we know that for the case of external flows, for us the concerned thing is whether the flow is laminar or turbulent. However, for internal flow, we must also be concerned with the existence of entrance and fully developed regions. Okay, so now it's not just laminar and turbulent flow, you also have to consider the entrance and the fully developed region. Look at it. This is a pipe, and the flow was uniform at the inlet. But what happened? Once the flow enters the pipe, the boundary layer starts developing at the top, at the bottom, all the sides. Boundary layer starts developing, right? So this is the inviscid flow region. Now the question arises, what is inviscid flow? You have gone through this in fluid mechanics so far. You should have. So inviscid flow region, inviscid flow.
Does it not ring a bell?
Does not ring a bell. Okay. Look, inviscid flow, when you have a viscous flow, we call it viscid flow. Inviscid is a non-viscous flow. Viscosity comes in effect when fluid flows in layers. Whenever there is a variation in the velocity of the fluid between layers, so there will be friction between layers. So that's viscosity, right? So when the fluid is moving at the same speed, all the layers moving at the same speed, will there be any friction between layers? No. Friction is there when you have a relative motion. If there is no relative motion, no friction. So this is inviscid flow. But once it enters into the pipe, now there is a velocity variation in this region. Now there is a velocity variation in this region, right? And velocity variation in this region. So this region where the boundary layer is developing no more is an inviscid region. So viscosity effects are there now. But the center portion still velocity is uniform, right? And this is inviscid. But if you see there, as the boundary layer keeps on developing, the inviscid region keeps on decreasing until a time comes when the inviscid region finishes. Now after this, there is no inviscid region. Throughout from the top to bottom, there is variation in velocity. There is not even a single region where we consider that the layers have the same velocity. Is it clear? So now there is no inviscid region afterwards. So till we have the inviscid region there, this region is known as the entrance region. Boundary layer is developing but not yet fully developed. A time will come when the boundary layer is fully developed, and that means it is now constrained by the other boundary layers, and that means it is now developed. It cannot change afterwards. Okay? And inviscid region finishes. There is no inviscid region at all. Okay? So when that time comes, then we will have the fully developed region. So before this point, entrance, after this point, fully developed. Okay? So in case of the pipe flows, this is also one parameter that needs to be considered. Not just laminar and turbulent. You also have to consider whether it's entrance region or is it fully developed? Okay. So this length, when the boundary layer is not fully developed, when there is some inviscid flow region still present, this region is known as entrance length. It will have a specific length. So that's the entrance length. Or we call it the hydrodynamic entrance region. Hydrodynamics deals with the velocity. Thermal deals with temperature. Okay? So we are not right now dealing with the temperature. We consider, let's say, the flow has the same temperature as the tube. The temperatures are same. Only the thing is that there is velocity variation because of the boundary layer. Okay? So till inviscid region is there, this region is known as hydrodynamic entrance region, and the length after which inviscid region finishes, that length is known as hydrodynamic entry length. Okay? And after that, it is fully developed. Whatever be the length afterward, it is fully developed. Do you understand the concept of entry length?
Yes.
Do you understand the concept of entry length? When the flow is developing, entrance region, when it is fully developed? Do you understand that or not?
Yes, sir.
Good. So we now, in the internal flows, we have to consider these factors as well. Okay? The existence of entrance and fully developed regions. This is the entrance region. After inviscid flow, okay, after the boundary layer has been fully developed, and that's the fully developed region afterwards.
So it's the same fluid in these two regions?
Same fluid. So suppose water is entering. Only the thing is that in the center portion, water has the same velocity throughout. Here you have velocity from 0 to, you can say this is the free stream velocity. So the free stream velocity exists in the entrance region. So in the inviscid region. Okay, but once inviscid region finishes, now no more free stream velocity. Get it? So what are the kind of velocities that we'll have? So we'll have free stream velocity, but that is only at the enter point or within the inviscid region. Okay? But after inviscid region finishes, now you have a complete velocity distribution. Right? So velocity starts from 0, becomes maximum at the center line, and then keeps on dropping, becomes back to 0 again at the other edge. Get it? So now you have the free stream velocity. We call it another velocity, which is the center line velocity. Center line velocity is the velocity at the center. It will not be equal to the free stream. It will be less than free stream because boundary layer is not fully developed. I mean, the boundary layer is not allowed to develop furthermore. Okay? It's not allowed to develop until the velocity becomes equals to free stream, as in case of the external flows, because it is constrained by the other boundary layer which mixes together. So they stop at a certain point which is less than free stream. However, that is the maximum velocity so far in the pipe. So that's the center line velocity. Okay? So you have the center line velocity, you have the free stream velocity, right? You have the velocity at the surface, which is 0, obviously. And then, since we know that we have a velocity variation, but most of the time we need a specific velocity at a point. So what we do is that we take the mean velocity at this point. Okay? So the mean of it would be what? A specific velocity which can be assumed to be constant throughout the entire, it's an assumed velocity. Okay, so consider it as a mean of all these velocities from 0 to maximum, then maximum to 0. Add all together, divide by this area, so you get the mean velocity. Okay, so that's the mean velocity. So how many velocities types you have? Free stream, center line, surface, mean. Okay, do you understand these terminologies? Okay. So the highest one would be the free stream. Then the lower one will be the center line. Then further lower will be the mean. Then lowest is the surface velocity. So when we know that when the fluid makes contact with the surface, viscous effects become important and a boundary layer develops with increasing x. The development occurs at an expense of a shrinking inviscid flow region. So the inviscid flow region is shrinking, shrinking, shrinking until it finishes, right? And concludes with boundary layer merger at the center line. So at the center line, all the boundary layer merge together. Okay. Following this merger, viscous effects extends over the entire cross section. So now there is no inviscid region. The complete is the boundary layer region. So viscous effects are there from the top to the bottom. There is not even a single region where the viscous effects are not there once it is fully developed. Okay. And the velocity profile no longer changes with increasing x. So now velocity profile is developed. So it's this shape. It's developed, and then it does not change at all. So initially the velocity profile was straight line, then it was like this, then after that it would be like this, then afterward it would be like this, and a time comes when it becomes completely like this, right? So it's fully developed. The flow is then said to be fully developed, and the distance from the entrance at which this condition is achieved is termed as hydrodynamic entry length. So entrance region is the length for that region is the hydrodynamic entry length. As shown in the figure, so what is the shape of the velocity profile? Parabolic. We should remember it is parabolic. Okay. For laminar flow in a circular tube. Okay. For turbulent flow, the profile is flatter due to turbulent mixing. So it's not a perfect parabola for a turbulent flow. Okay. So parabola shape is like this, right? So if you take a hammer and put it like hammer it a little, so it will become a little flat. Okay. So it's a little flatter, still close to parabolic, but not parabolic. Okay. So that was about the hydrodynamic considerations. Okay. We need to add that camera. Okay. Now let's talk about the thermal consideration. Hydrodynamic consideration over. You understand? Thermal consideration exactly in the same pattern as hydrodynamic consideration. Now the disturbance in the temperature. So let's say the temperature of the free stream is different than the temperature of the pipe. Okay. So what will happen? A boundary layer, thermal boundary layer will start developing. Now this is the thermal boundary layer that starts to develop. And again the same thing, a time will come when there is no region where there is so here there is temperature gradient, here there is temperature gradient, but there is a center region where there is no temperature gradient. So a time will come when there will be no such region where there is no temperature gradient. Throughout you will have a temperature gradient from top to bottom. Okay. So suppose the surface temperature is high. So top will be the surface temperature and bottom will again be the surface temperature, and these will be the high temperatures. Okay, but the temperatures will fall until it reaches a centerline temperature. Okay, and you have a T infinity temperature here. Okay, but if you want to know the temperature at a specific cross section, so you will take the mean of, you will not consider this variation, you will take the mean of it. So you will have a mean temperature here, T mean. Whenever we say T mean, it means that there is variation within the temperature at that one section. So if I cut a section of the pipe, within that section you will find at different points you will have different temperatures. But we take the mean of it because we want to know the temperature at one point, at one cross section, one temperature. So we take the mean. Okay, so that's the mean temperature. So in this case, suppose that the surface temperature is high, okay, then the T infinity. So the highest temperature will now be the surface temperature, okay. Below that will be the mean temperature. Center line temperature would be less than the mean, and the lowest temperature would be the T infinity. Right? Suppose T infinity was 20 degree and T surface is T infinity was 20 degree. Okay, here. T infinity was 20 degree, surface was 100 degree. Right? So center line temperature will not be 20 but will be slightly higher than 20. Okay, so suppose center line is 30. Okay, so but the mean is between surface to center line. So it will be, say, suppose 70. Right? This is for the case if the surface temperature is less. If the surface temperature is high, switch. Okay. So this is for the case if the surface temperature is high. If the surface temperature is less, switch. Okay. Anyways, so you do understand the term. And similarly, when the boundary layer, thermal boundary layer, is fully developed, so the entrance region for that is known as thermal entrance region, and the length is thermal entry length. Okay, and then we'll have the fully developed region. So this is for the thermal consideration. Last one was for the hydrodynamic consideration. Hydrodynamic consideration deals with the velocity. Thermal considerations deals with the temperature. Right? So, do you understand the concept of free stream, surface, mean, center line, velocities and temperature? Do you understand the concept of entrance region and fully developed region?
Yes.
Is there anything that you don't understand? Okay.
Why is the thermal boundary layer flipped?
Why is the thermal boundary layer flipped? What do you mean by flipped?
The velocity boundary layer was.
Okay, the velocity boundary layer was like this because the velocity was 0 here, but was increasing. Now, in this case, we consider that the surface temperature is the highest.
If it's the lowest.
Suppose if it is lowest, okay, then it will be the temperature profile would be exactly the same as the velocity profile. Okay, so then it will be like this. Only one difference. In the velocity profile, this point is 0, this point is 0. In the temperature profile, this point and this point are not 0. This point and this point are the surface temperatures. Okay, so in the velocity profile, you draw a line here. In the temperature profile, you draw a line somewhere here, and these are the temperatures, just to show that this is not 0. Okay, you get it?
Yes.
Okay. What is the surface velocity in the previous one?
Surface velocity here, 0.
It's always
0.
zero. So the mean velocity is higher than the surface velocity.
Yes, definitely. Yeah, there is one thing. Mean velocity will always be higher than surface velocity, but let's say if your pipe is moving, then the surface velocity is not 0.
Is there a pipe to that?
Yeah, there are pipes that moves. You have a car, inside the car you have the piping, and the car is moving. Don't worry, we are not going to deal with those situations here in this course.
Still, in this case, the mean velocity is higher than.
Still.
Why you write here surface before the mean?
No, I write it here, but I said it otherwise. I do not write it in the order of increasing or decreasing. So is it clear? These are some of the questions you can answer yourself since you are experts. Okay, the mean velocity, or that's the concept of the mean velocity. I already explained you the concept of the mean velocity. Okay, so what we do is that we have a velocity profile and we want to know what is is the mean velocity at that point. Okay, so if we take the mass balance, or if you write the formula for the mass flow rate formula is what? M dot is equals to rho AV. Remember that formula from thermodynamics? M dot is equals to rho AV. Yeah, sure, you remember it. Okay. So it was M dot is equals to rho V dot, or volume flow rate.
Yes.
Okay, and volume flow rate is basically AV. So I think volume flow rate, we put it as Q there. I don't remember what symbol we used. So V dot is basically AV, cross section area into velocity. Okay, and I also asked you to prove it based upon the units. Put the unit of area, put the unit of velocity, see does the unit of volume flow rate matches. We did not make videos for thermodynamics. Anyways, so you have the mass flow rate. Okay, but just remember this formula. This is a very common formula and you'll be using it a lot. Okay, so although this formula, we can't put it in the book of formulas, but yet this is something that you should remember. Okay, so we have rho into area, cross-section area, into velocity, but the velocity is changing with the radius. Okay, so we can put it in the differential form and then integrate it. Okay, so then we can find out what is the mean velocity. So the mean velocity will come out to be something like this. This is a simple integration. You can go through it yourself. There is nothing to spend more time on it.
Doctor, it's here. It's go back and forth.
Oh, really?
No, it's come back to the.
Okay. Okay, so if we want to find, similarly, we can find the mean temperature. Okay, the mean temperature, because there is temperature variation across the cross section, and we want to find one temperature for it. So the mean temperature, what do we do is we do the energy balance. Okay, so energy is what? E equals to mCp T, mc delta T, right? So it's mCt is the energy. Delta T will give you the change in energy. Okay. So by considering that formulation, so now T is varying with the cross section. Okay, so M we can put it as rho V, okay, or M dot we can put as rho AV. Okay, so T is varying with the cross section across the radius. So put it in the differential form, then integrate it. So we can find out what is the T mean. So T mean will be this thing. Anyways, this is again simple integration, and you're actually not going to be using it much in the numericals. So Newton's law of cooling is Q is equals to or heat flux is equals to H Ts minus T mean. So at any specific point, if you want to know that how much is the heat transfer, so you have a pipe, okay, so you have a pipe and the flow is going through the pipe, okay, at any point if I want to know what is the heat transfer, so it will be Q is equals to H A delta T, okay, where delta T will be what? Surface temperature minus the mean temperature, or the mean temperature minus surface temperature based upon in which direction heat is flowing. Okay. Okay. Thank you. Hydrodynamic and thermal entry lengths. So now from here, the formulas start, and then there is just formulas. This course is filled with formulas. I think you'll have a formula book this thick. Okay, so you'll have a table of formulas after some slides. Okay. Reynolds number. Reynolds number is what? Rho Vd upon mu, right? So Reynolds number is rho Vd upon mu, or we're talking about this velocity here, okay? So this velocity will be what? It should be the mean velocity. Sometimes velocity they write it as v, sometimes they write it as u, but you can understand it means velocity. So here they wrote it as u. Okay. So u mean velocity. So that will give you the Reynolds number. We'll talk about the diameter. Okay. So this d is the we call it hydraulic diameter. It has a different name because it has a different formula. This d is not just the diameter, we call it hydraulic diameter. There is somewhere written here.
Yes.
With red.
Hydraulic diameter, right?
Yeah.
See? This is a hydraulic diameter. So call it dH, and it has a formula, and the formula is 4 into cross section area divided by P. P is the parameter.
The surface area.
Not area. Parameter is the length. So in a cross section, what is the length of the surface? Okay, so it's not area. Parameter is the length. Okay. Now, if you because the thing is that we are considering internal flow. It's possible that internal flow is within the pipe. Okay, but there is a possibility that the pipe is circular. There is also a possibility that the pipe is rectangular. Maybe the pipe is not even rectangular, maybe the pipe is triangular. Okay, maybe the pipe is octagonal, hexagonal. Sometimes happens. Okay, so if this is the case, that the pipe is not a circle specifically, then what should be the d? Okay, so we found it as hydraulic diameter. For the circle case, let's see what is the d. Hydraulic diameter is 4 multiplied by cross section area. What is the cross section area for a circular pipe? Pi in terms of the diameter, let's say. Pi over 4 d square. What is the parameter? Interval diameter. Pi d. Good. So 4 will cancel with this 4. This pi will cancel with this pi. This d will cancel here. So what's left? D. So for the case of circular pipe, hydraulic diameter is the diameter. But if it is not a circular pipe, then it might not be the diameter. It might be some other value. But it's coming out of this formula. 4AC over parameter. Is it clear? That's the hydraulic diameter. So we discussed about this thing. So this is dH. Okay, 4. Reynolds number. Reynolds number, it's the same formula, but we can write it in terms of the mass flow rate as well. Okay, for a circular pipe, the Reynolds number, if we want to write in terms of the mass flow rate, it will come out to be 4 m dot over pi d mu. Can you do it? Can you prove it? So Reynolds number is equals to rho v d upon mu, right? So m dot is what? M dot is rho AV, or instead of putting v, let me call it here u, because okay, I put it there v, so fine, v is okay. Okay, so rho into v is what? Rho into v is m dot upon a, right?
Yes.
So instead of putting rho into v, I can put here m dot upon a, and d will be what? 4 a upon p, right? And mu is here, right? So this a will cancel with this a. 4 m dot p is what? Parameter. For a circle, parameter is pi d, right? Instead of putting p, let me call it pi d here. So did you get the same formula? 4 m dot upon pi d mu. For the case of for the case of pipe, Reynolds number can be written as this. For this formula, it's a very simple formula. You can drive it, Okay, I derived it here for you. But most of the time what happens is that for the case of pipes, mass flow rate is given. So it's better to write the Reynolds number formula in terms of the mass flow rate so that we can use directly mass flow rate to find the Reynolds number. Here it's not mass flow rate. Most of the time in the problems it's like that, with 1 kg per second mass is flowing through the tube. Find the Reynolds number. So finding the Reynolds number directly using a formula using mass flow rate is like this. Okay, so in case of the internal flows, the onset of turbulence occurs at a critical Reynolds number 2300. So the critical Reynolds number here is 2300. Below 2300 it will be laminar. After 2300, turbulence will start to occur.
So here is the transition point.
So consider it as a transition point. At around Reynolds number 10,000, it is fully turbulent. It's clear? Hydrodynamic entry length. There is a formula for hydrodynamic entry length. Hydrodynamic entry length, you know what is hydrodynamic entry length.
Yes.
It's the entrance region for the velocity profile developing. Okay. So that length, how much is that length? That length has a formula for laminar flow and for turbulent flow. Okay. For laminar flow, that length has a formula x is the length, consider this as the length, FD, fully developed, comma H means hydrodynamic. That means this is the length for fully developed flow for hydrodynamic case, divided by D is approximately equals to 0.05 into Reynolds number. So if you know the Reynolds number multiplied by 0.05 multiplied by the diameter, you will get this length. This is the length of the entrance region
Multiplied by the diameter?
because it is x by d.
Oh.
X is the length. You know, we always put in terms of the dimensionless parameters. So x is a length, it has unit meter, diameter has also unit in meter. So now it's dimensionless if you put it x by d. But we want to find x, so x is equals to 0.05 into Reynolds number multiply by diameter, right? If it is laminar case, right? If it is laminar case. If it is turbulent case, then you do not use Reynolds number. If it is turbulent case, then we do not use the Reynolds number. Then it is what? X FD, or you can say this is the formula. X by D is equals to 10.
I know the diameter.
Just know the diameter, multiply the diameter by 10. This is the entry length if the flow is turbulent. You eventually first need to know the Reynolds number to know if it is laminar or turbulent. Okay? If it is laminar, then multiply with the Reynolds number 0.05, multiply by the diameter. That's the entry length. If it is turbulent, then no need for the Reynolds number. Just multiply diameter by 10.
What's the difference between the thermal length and hydrodynamic?
The hydrodynamic length is for the entrance region of the velocity, after which the velocity profile is fully developed. The thermal entry length is for the case for when the temperature profile is fully developed. You remember we discussed two cases,
Yes.
hydrodynamic, thermal. So the entrance region for the hydrodynamic case is the hydrodynamic entry length. That's the velocity variation when the inviscid region finishes. Okay, and this is for the next one is for the thermal entry length. If you see here, the formula of thermal entry length is almost similar to hydrodynamic entry length, only the difference is that here we put Prandtl number as well. So if you know the hydrodynamic entry length, Now this is an important point. This is an important point. So hydrodynamic entry length is what? 0.05 into a Reynolds number, right? If I put this here,
You just multiply.
so just multiply the hydrodynamic entry length with the Prandtl number, it will give you the thermal entry length. See here? This is an important point. The formula for the turbulent flow is the same. No difference. So this is the same. Whether it is thermal entry length or hydrodynamic entry length, formula for the turbulent flow is same. Do you understand the concept so far? Is there anything that you do not understand? I'm moving a bit slow because these are all new concepts. So if once you get used to it, then we'll move at a steadfast speed. Anybody has any question, you can ask.
This will be in the formula, right?
Yeah, all will be there in the formula sheet. In the formula book.
We lost it. Yeah, it is not.
Yes.
The other formula of turbulent.
Same formula. So this is one formula. You see here, for turbulent case this, for turbulent case this, both same. So if whether it is the hydrodynamic entry length or it is the thermal entry length, they have the same formula if it is the turbulent case. Okay, the next is what may be said about the variation of mean velocity with distance from the tube entrance for steady constant property for flow? It remains constant. So once the profile is developed, then the mean velocity remains constant, does not change. Mean velocity is changing until the velocity profile is fully developed. Once it is developed, then the mean velocity will remain changed throughout the length of the pipe. Okay. Now pressure drop is another important parameter. As I told you, this is because this is something that directly deals with the economics. Okay, how much pressure drop is there, because this is for the flow to occur, for the heat transfer to occur, you need the flow. For the flow to occur, you need to have the pressure difference. But there will be pressure drop occurring. Okay. So how do you provide that pressure energy? It's by using pumps, by using fans, whatever. Okay. So, but how do we run the pumps and the fans? By electricity. And how do we buy them? The electricity is bought by the electricity authority, and the pumps and fans are bought by the market. And how do you buy these things? You need money. Everything goes back to the economics. So pressure drop is a very important parameter for all the heat exchanger problems. For all the heat analysis, pressure drop is a very important phenomena. It's a very important parameter. So let's talk about the pressure drop through the pipe. Okay, so the pressure drop through the pipe is determined by this formula. Now how do you come up with this formula? I leave it to you for fluid mechanics. You're going to go through it in fluid mechanics, that how do you came up with this formula. Okay, so it is the friction factor is equals to negative dp by dx. Negative dp by dx. Why? Because if the flow has to occur, the pressure must drop in the direction. If the temperature has to, if the heat has to flow, the temperature must drop in that direction. Right? This is same concept. So if the flow has to occur, the pressure must drop in that direction. So fluid always flow from high pressure to the low pressure. So that's why dp by dx itself will be negative. So negative multiplied by the negative will become positive. Okay. Multiply by d, diameter, divided by rho, whatever the density of the fluid which is flowing, multiply by um, mean velocity square by 2. So rho v square upon 2. This is also a very important parameter, rho v square upon 2, because you are using it many times at many places. Why this combination is used? That's the dynamic pressure. This again I leave it to you for fluid mechanics.
Right.
Okay. So that's the formula. Okay.
Of the friction factor.
Or the friction factor. But if you know the friction factor, you can find out the pressure drop. This dP is the pressure drop, right? So if you know the friction factor, you can find out the pressure drop. Now friction factor has formula. For laminar flow, friction factor formula is this: 64 upon Reynolds number. These are empirical formulas, came out by experiments. For turbulent flow, we use the Cole-Brooks correlation, which is this formula. Now in this formula, this is an implicit type of a formula. You cannot separate F on one side. It's not possible. So, but this formula is there to determine F. This formula is there to determine F. But that was for the laminar case. This is for the turbulent case. But for the turbulent case, the formula is such that you cannot separate F on one side.
How to get the value?
How to get the value? It's a problem of mathematics, right? No, you don't have to deal with it. Okay, what we need to do is that you will not be using actually this formula most of the time. You will be using a Moody chart.
Yeah,
Moody chart. Okay, it's Moody. Moody or Darcy. Yeah.
better.
Moody chart. So the Moody chart is this one.
We came back to the...
No. Actually, this is a very important chart, and like for example, if somebody says that I have taken the course of heat and mass transfer and I want to know, okay, do he really know the subject? I will just ask him, okay, tell me what is the Moody chart. Do you read it? Okay. It's not main objective of the course, but this is something that a student must go through while going through this course. Moody chart is very important. And this Moody chart you are also going to deal with in the fluid mechanics as well. Okay? So it's going to help you there as well. So let's study this Moody chart. First of all, do you think it's a linear chart?
Log chart.
It's a log chart, but both x and y axis are log, or just one axis is log, other is not log?
Both are log.
Both are log, yes. How do you determine both are log?
There is 3 axes. There is 3 axes.
Is there a third axis?
Yes, and then right. This is the number of the lines.
These are the number of the lines, not the third axis. If there was third axis, then third axis would be in the 3D dimension. It cannot be on this side. Okay. So let's discuss this Moody chart. So in the Moody chart, what we have here on the x-axis is the Reynolds number. Okay, is there a way I can zoom in?
The 3 dots.
3 dots.
Really? Screen? No. Okay, leave it.
Off of the slide.
Now we will zoom.
Zoom from the corner, right corner, below.
Oh yeah, okay. Okay, good. Assalamu alaikum wa rahmatullahi wa barakatuh.
Breakfast, lecture. Good morning.
Good morning. Okay, let's read this Moody chart first. Okay, we have the Reynolds number on the x-axis. You can see, right? So Reynolds number 10 to the power 3. Then it's written 2, 3, 4, 5, 6, 8, 10 to the power 10, 4. What is it? 2, 3, 4, 5, 6,
Number.
2 to the power.
2 to the power that. Okay. So here it means 4 into 10 to the power 5. Then 5 into 10 to the power 5. 6. 7 is there in between. 8. So 7 is there here. 8. 9 is there here. Okay. And 10 to the power 6. Like this.
But what's Moody chart?
That's the Moody chart.
What is the objective?
Objective is to find friction factor. If you
Why
know,
you said that it's important for who study hydrodynamics?
because as I told you, pressure difference or pressure drop in pipes are very important. This is, look, for when you go for the heat exchanger, suppose you want to go to the market to buy a heat exchanger. What are the two things you will ask? Okay, so you will ask, how give me a heat exchanger of that size which can transfer, suppose 50 watts of heat, and the pressure drop should not be more than this much. So these are the two parameters which you will be using to buy a heat exchanger from the market. Okay, so pressure drop is a very important parameter, and what is the actual amount of heat transfer is a very important parameter. These are the two parameters which are the defining parameters for a heat exchanger. Okay, without one of the two parameters, the definition is not complete. Okay.
Okay, yes. So for the numbers on the left of the 10 power 6, we multiply it by 10 power 5, right?
Yes. Thank you.
I want to.
Okay. So the objective of the Moody chart is that you find out the friction factor. Okay. So this is the x-axis. Then you move up, and you'll find multiple lines, right? So many lines here, and these lines are what? These lines are for the relative roughness. Relative roughness is, as the word represent, how rough is the pipe. Okay, so if you have a pipe of concrete, it will be very rough. If you have a pipe of plastic, it will be very smooth. If you have a pipe of steel, glass, very, very smooth. If you have a pipe of steel, if you have a pipe of copper, brass, aluminium, they have different roughness. Okay, so that's the roughness parameter. Okay, so the relative roughness is E by D. Again, it's a dimensionless parameter, E by D, where E is the roughness, and it is measured in micrometer. Diameter is something, whatever is the diameter, but E is the roughness, which is measured in micrometer. It means how much is the rough, how much is the up and down in the pipe. Okay, it's written here, if it is a drawn tubing, then it is 1.5 micrometer roughness, E. Okay, if it is a commercial steel, then it's approximately 46 micrometer. Okay, what is drawn tubing? If the pipe is made such that it is made by the extrusion process, leave it. if it is cast iron, the roughness is 260 micrometer. If it is concrete, the roughness would be between 300 to 3000 micrometer. Okay, but anyways, this is the relative roughness. Okay, suppose you know what pipe you are using. So roughness is a parameter of the material. So change the material, roughness will change. If you know what pipe you are using, if you know what is the Reynolds number, so suppose you are using a cast iron pipe, okay, for a diameter 10 millimeter or 10 millimeter very small, say 50 millimeter diameter, okay, this is also very small, 100 millimeter, okay, 100 millimeter diameter. So you will find E by D. E is in micrometer, diameter is in millimeter. So you will know what is the relative roughness. So if you know the flow is inside this pipe, you will know what is the Reynolds number. Suppose the Reynolds number is this. So you will go to that Reynolds number, then move on to these lines. Which line you will select? Which is according to the roughness. So suppose that if your roughness is 0.0015, so it is 0.001, this is 0.002, but 0.0015 would be in between the 0.001 and 0.002. So you will make a line here, almost, which is in between these two lines. Then you will intersect your Reynolds number to that line and then go in this direction to find out what is the friction factor. You get it or not?
Yes.
You see here this dotted line? This dotted line is a transition line from laminar to turbulent. Okay? So this region, you can see this is a fully rough zone.
And we can't check
Yeah, you can check.
our answers.
Okay, then we have if the roughness is, if it is said that it is, for example, it is a glass pipe or it is a very smooth pipe, it is just said that it is a smooth pipe. For the smooth pipe, you have the last curve. The very last curve, it's written here, this is for smooth pipe. Smooth pipe means there is no roughness at all, zero, right? So if it is said that for a smooth pipe, find out the friction factor at specific Reynolds number. So you'll go to that Reynolds number, go to the smooth pipe curve, which is this one, and then find out friction. Okay. This I made a mistake. This is not turbulent to laminar transition. This is fully rough zone to partially rough zone. Okay. So in this region, if you see, in this region, the relative roughness is high compared to this region. Laminar is this line. If the flow is laminar, you had that formula 64 upon Reynolds number,
Yes.
right? So it's a straight line, 64 upon Reynolds number. That's the laminar, 64 upon Reynolds number, right? And these are all for turbulent. This is all for turbulent. Okay. So
The laminar flow, whatever the pipe is.
for the laminar for whatever the pipe is. Okay. So is it clear? Do you understand this Moody chart now?
Moody.
Yeah, this Moody chart. So you know the Reynolds number, you know this relative roughness, you can find out what is the friction factor. Okay. For the laminar flow, this line. For the turbulent region, all this. Okay. And these are the relative roughness, and this is for the smooth pipe.
The difficult is read the number of x-axis here.
It's okay. It's not difficult. It's reading the log table. That's it. If the chart is good enough, big enough for you, you can read it. And if there is error in reading, error which is less or acceptable,
In that region, it's okay.
in that region it's okay. If you want exact value, then instead of using the chart, we use the formula. But using the formula is a bit hard, because for the implicit formula, it's very hard to find the value.
They would use the both of them with error.
Can you have a brain transfer?
So once you know the friction factor, then you substitute it in the formula, find out the power. So once you know the friction factor, you substitute in this formula, find out the pressure drop, And once you know the pressure drop multiply by volume flow rate or mass flow rate divided by density, this will give you the power requirement. Okay. So these two formulas you will be using also. Anyways, these two formulas will be there in your book of formulas. Okay, so is the concept for the finding pressure drop using Moody chart, these things clear? These things will also help you out in the fluid mechanics as well. Okay, when you have fully developed thermal flow, okay, so when you have thermal flow fully developed, that means in the fully developed region, then the heat transfer coefficient does not vary after that. Heat transfer coefficient becomes fixed. So you see, initially when it is developing, heat transfer coefficient drops, but once it becomes fully developed, then the heat transfer becomes constant. Okay, so this is a property that you should know, and this graph you should remember. Okay, this graph you should memorize, just to know that for the case of internal flows, after fully developed flow, it becomes constant. Heat transfer coefficient becomes constant. Okay. Now, for determining the mean temperature, okay, or there is one important concept here. What's the time here? It's 9:24. Okay, there is one important concept here. So you have a pipe, and suppose the pipe is heated, it's hot, and you are making a cold fluid to flow, cold water is flowing. Okay, so as per the energy balance, the amount of heat convected by the pipe is equal to the amount of energy increase in the water, right?
What?
So I have a hot pipe, and cold water is flowing through it.
Cool.
Cold water is flowing. So let's say the pipe is 100 degree, and the water is 20 degree.
The pipe or the water in the pipe?
No, pipe is 100 degree. Pipe is hot.
Okay.
Okay, somehow we are heating it.
Okay.
Okay, pipe is hot, and water is cold. So as per the energy balance, the amount of heat convected by the pipe is equal to the amount of heat energy gained by the water.
Okay.
Game.
Make sense?
Yes.
So amount of heat convected by the pipe is what? Q is equals to HA delta T, right?
Yes.
Amount of heat gained by the water is what? Q is equals to m dot Cp delta T,
Yes, sir.
and they both are equal. As per the energy balance, the amount of heat convected is equal to the amount of heat gained by the water.
Chapter 2.
For thermodynamics?
Not here.
Yeah, maybe.
Convected and.
Yeah,
radiation
yes,
and
yes.
everything.
Do you understand this concept? Because we are going to be using this a lot. So that means HA delta T is equals to m dot Cp delta T. But what about these delta T's? When we are saying HA delta T, so what delta T we mean?
Mean and surface.
Mean and surface. Q is equals to HA delta T, so that's the amount of heat convected from pipe to water. So the temperature difference between pipe to water, that is important, right? That is this delta T. What about this delta T, m dot Cp delta T? So this delta T, m dot Cp, is the amount of heat gained by the water. So now we are only concerned with the water. What was the initial temperature? What is the final temperature
Yes.
of the water? So the two delta T's are different.
What is the first one?
The first one is the amount of heat convected.
Yes.
So delta T will be the temperature difference between the pipe and the water.
Not the surface or the out there. Out.
No, we are considering the convection from the tube to the water,
Okay.
right? So that delta T will be different from this delta T.
But there is convection between the air and the pipe.
Yeah, there is convection there as well.
Uh,
We are right now considering only this.
Turbulent flow.
We are considering the internal flow. But this is a very good point because we have a slide for it as well. We are going to come to it.
What about the radiation?
We can include it. We can include that as well. No issue. Do you understand this concept? So this is the main concept in here. So amount of heat convected is equals to the amount of heat gained by the water. Amount of heat convected is equals to the amount of heat gained by the water.
Okay, I will know if it's like this. If he said it's internal flow. Then if
Don't
in the
worry,
final,
it's-
I will get.
Don't worry, you will know everything. Just let it flow. Okay. Now using this concept, we can find out, now we have two cases. One case is if you have a pipe, previously we discussed those cases as well, constant surface temperature case and constant heat flux case. Suppose you have a pipe and the condition is that the heat flux is constant. So the surface temperature might not be constant. As the fluid is flowing through the pipe, surface temperature of the pipe is not constant, but the heat flux is constant. Okay? Or there could be another case in which we are not talking about the heat flux, but what we say is the surface temperature is constant. So as the fluid is flowing through the pipe, the surface temperature of the pipe remains same. Okay? What could be the condition surface temperature of the pipe is remaining same? Suppose there is condensation occurring at the top. So condensation occurs at the same temperature, so the surface temperature at the pipe remains constant. And for condensation, heat has to be rejected. And suppose this rejection heat is taken by the fluid which is going inside the pipe. Okay? So the pipe temperature would remain constant in this case. Right? And what is the example of a constant heat flux? Suppose you are taking solar energy. So you put a pipe in the sun, so the heat flux from the sun is constant throughout. Constant means throughout the length it is constant. Okay, so that's an example of constant heat flux. The condensation was an example of constant surface temperature. Right? So now for those two cases, putting these equations, we can find out the mean temperature of the fluid. So the mean temperature of the fluid, if it is a constant heat flux case, if it is a constant heat flux case, is this. T mean is equals to T mean inlet plus, this is the heat flux, constant heat flux, multiplied by P means parameter. P means parameter of the pipe, divided by m dot Cp into x. So suppose you have a pipe with a constant heat flux. The heat flux is constant on the pipe, right? That is Qs double dash. Heat flux is constant and the fluid is flowing inside the pipe. Okay, and suppose I know what is the T mean inlet. Mean inlet temperature I know. Now if I want to know that after passing a length of x meter, what is the T mean temperature here? So that will be T is equals to T mean inlet plus whatever the it's not necessary T, it's actually not T infinity, because the pipe, yeah, you know, sometimes, for example, assume that this is the room and a pipe is coming from that wall to this wall. Okay, so it's not actually that the water is entering in the pipe at that point. The pipe is a closed circuit, so it's flowing continuously, right? So that means there it is the T mean inlet. It's not T infinity. Okay, it's not coming from outside and entering into the pipe. When we talk about T infinity, it means water entering from outside into the pipe. But if it is already in the pipe, it's T mean. It's not T infinity. Okay, so T infinity we consider not inside the pipe, outside the pipe. We consider T infinity as outside the pipe. Okay, so there is no free stream now. So we have the T mean inlet, suppose we know, So we know T mean inlet plus QS, whatever the heat flux, this is a constant heat flux problem, multiply by the parameter, whatever the parameter of the pipe, pi d, if the pipe is circular. If it is not circular, then whatever the parameter. Divide by m dot, say you know the mass flow rate, multiply by Cp, specific heat of water, multiply by x, how much length pass, right? So you know that at this point, what is the T mean temperature? Is it clear? So this formula will be there in the book of formulas, okay? And this graph is very, very important. This graph shows what? If it is a constant heat flux, so the T mean will continue to increase. T mean at inlet will be initial, then as it passes through, as the fluid continues to flow in the pipe, T mean will continue to increase because you have a constant heat flux, right? So T mean will continue to increase in a linear pattern, and T surface will also continue to increase, but in the entrance region like this, and after it is fully developed. So after a fully developed, T mean minus Ts would almost become a constant. This difference would almost become a constant. Almost parallel line. So Ts minus T mean would become almost constant in the fully developed region, right? This graph is basically the temperature variation in the axial direction. This is the axis of the pipe. This is the axis of the pipe, right? In the axial direction, temperature variation for constant heat flux case. This graph is the temperature variation in the axial direction. So here the length is 0, here the length is x, and continue so forth, okay? For the constant heat flux case. So that's how the temperature variation for the mean fluid temperature will be there. That's how the temperature variation for the surface temperature will be there, assuming surface temperature is greater than mean temperature. So this graph, consider it as a very important graph, okay? Do you understand this graph or not? Do you have any question?
Which one for the surface, which one for the fluid?
Ts is for surface.
For surface it will increase?
Keep on increase because you are supplying heat flux continuously.
You didn't say it is cool water?
Water is cool.
Okay.
Cool water in terms of with respect to the surface. Water is at low temperature with respect to the surface.
No.
So, yes.
It will increase? If
Yeah.
it's cold water, it will increase the temperature?
Because of the heat flux, constant heat flux.
There is a...
So the constant heat flux is going to raise the temperature of the pipe and the water. Is it clear? Constant heat flux is going to raise the temperature of the pipe and the water. Do you think that when you are supplying heat, suppose you put a pipe in the you put a water in the pipe and put it in sun, do you think the water will become hot and the pipe would remain cool?
No.
Both will rise.
No, there is heat flux.
There is heat flux, constant heat flux. That's why I say this is important, because if it is not constant heat flux, then you have a different profile.
Yes.
Okay? So this is for the other case. If we do not have the constant heat flux, if we have a constant temperature of the surface.
Okay.
So if we have a constant temperature of the surface, then this is the temperature distribution. So surface temperature would remain constant, Ts. But T mean will keep on rising from inlet to outlet, but at any point T mean will never be the same, or will never increase by Ts. It will always be at the lower side. Okay? So it will increase like this, but will never become equal to T mean, T surface. T mean will never become equal to T surface, or become very close to T surface if it is a very long pipe. Is it clear? Now in this case, if this is the case, then this is the formulation. So suppose that now you do not have a constant heat flux. There is no constant heat flux. There is no constant heat flux. But now there is a constant surface temperature, Ts. This is constant. This surface temperature is constant. Okay? And suppose after a distance x, okay, we need to know what is the temperature, T mean. So consider this as T mean outlet. This is T mean inlet, T mean outlet. Okay? So T mean outlet will be equals to T surface minus T mean inlet exponential negative H As upon m dot Cp. This is for the case of constant surface temperature. Previous formula was for the case of constant heat flux. Again, this formula will be there in the book of formulas. And these formulas are derived by the same concept, that the amount of heat convected is equals to the amount of heat energy rise in the fluid. These formulas are derived using the same concept. Amount of heat convected is equals to the energy rise in the fluid. And from this here, we come up to this formula, delta T Lm, which we already went through before, log mean temperature difference. So delta T outlet minus delta T inlet divided by Ln delta T outlet upon delta T inlet. Okay? If we want to know what is the overall heat transfer, so overall heat transfer from the pipe will be Q is equals to HA delta T. But the question is that we do not want to know how much is the heat transfer at this point or this point or this point. We want to know overall how much is the heat transfer. So we will use the overall surface area, right? But the H, so the H we will get will be the average heat transfer coefficient. But what delta T we are going to use? So it will be the log mean delta T. Because here delta T is different, here delta T is different, here delta T is different, here delta T is different. So from inlet to outlet delta T's are different. Okay? So, but whatever the inlet delta T we know, whatever the outlet delta T we know, based upon that we will find out what is the log mean delta T. This log mean delta T we are going to use here to find out the average heat transfer coefficient. Suppose if we don't want to know the average heat transfer coefficient, if we just want to know that at this point, at this section, what is the heat transfer? Okay, so it will be Q is equals to HA delta T, but in this case this delta T will be T surface minus T mean at this point only. Is clear? Then the H we will get will be only at this point, not the overall average.
The area will be the cross section.
And this area would be what? So it will be the parameter. Area is the area across which heat is being transferred. H.
So surface area for this region.
Yeah, surface area for this region will be the parameter only, because we are considering this section, so there is no length here. So just the parameter. It's clear?
And the parameter is only meter.
Meter. Yeah. So here you will not get, so here you will get Q upon L, consider. Is it clear? So again, this graph very important. One for the case of constant heat flux, one for the case of constant surface temperature. Okay. This H bar upon AS upon m dot Cp, this is also known as NTU, number of transfer units. You're going to deal with it in a much more detail in chapter number 11. But anyways, this is a very important parameter. Number of transfer units, NTU. Okay, it is this term. And you will see that if you put this term equals to 5, approximately Ts will become equal to T mean outlet. Very close. T mean outlet would be very less, smaller, less than 0.1% difference between T mean outlet to Ts. So this will become almost very close to Ts, okay, at NTU about 5.